Okay, so this is an introductory course on computer graphics where we will deal with some basic and fundamental principles of computer graphics. So as it says, my name is Prem Kalra. The best way to contact me is through the email address which is there, and you can contact me from anywhere then. Okay, so let's try to see the administration of this course, right. So as we know that this is in a slot J, Monday, Wednesday, Thursday at 12. So as far as the evaluations are concerned, it's going to be based on exams, where we have 2 minor exams, let's say between 30 to 35% of the grade, and a major exam which may be of 30%, right. And then we have projects or programming assignments, 3 to 4, right. We will have 35 to 40% of the weightage. Okay. So as I tell everyone that this is the most essential component of the course, right. So you must do the assignments if you want to learn the course properly. Okay. So this is the TA who is going to see the demonstrations of your assignment, and this is a web page of the course. So in case any announcement or the slides for the course are available on this website. Okay. So let's see now the books and the material which is going to be used. So most of these are sort of reference material. So I will be referring to collection of these books and material. And if you see here that this book by Foley, Wyndham and others, and the computer graphics book by Hearn and Baker, they are in international edition, right. So the cost of these books are not so high. So if one wants to buy a book which contains most of the syllabus we are going to cover, can buy one of these, right. And these are available in international edition, therefore they are affordable. And these are other books from where we will pick some material. Okay. Again, as I said, that all this is available on the web page. Okay. So let's look at the broad overview of the contents which we are going to talk about in this course. Okay. So first of all, we are going to look at some introduction and preliminaries of computer graphics, see also motivation of why one should study computer graphics, right. What are the applications of computer graphics? Then we will talk about what we refer to as raster graphics. So raster graphics basically is required because when you look at most of the display devices these days, they are nothing but collection of raster points which are pixels, right. So one needs to have the display in these devices. So what does it take to have the display on such devices? Involves certain techniques to be followed, and which we studied in raster graphics. Then there is concept of clipping, right. So clipping is basically something which is to identify what is of interest and what is contained in a zone which is of interest for displaying, right. So you clip entities or primitives according to the region of interest you have for the display. Then we are going to look at transformations. Transformations, you must have seen these transformations, the transformations like rotations, scaling, right. These are known transformations. So how these transformations are used in the context of computer graphics. Okay. And these are going to be both 2D and 3D transformations. Then we are going to talk about some of the representation schemes and the way to do modeling, right. So, curves and surfaces are basically methods which or representations which give us indication how can we model objects. Okay. And then we have rendering, which is how do we display the models, and then possibly looking at the movement of those models. Right. That is what gets captured in animation. Okay. So, this is the broad, let us say, contents we have. Okay. So, if you look at say the definition of computer graphics, so you understand maybe by seeing many examples of computer graphics what it could be possibly, right. But just let us say if we want to see as a definition, then it could be basically a way to use computers to define, to store, to manipulate, to interrogate and present, that is display pictorial output. Okay. So, these are some of the essential functionalities we have, which we address in computer graphics. Okay. And the motivation is to have a pictorial output is, as we all know, that a picture is 10,000 worth words, right. So, if you want to narrate a story or a scene or a situation, then if you give a picture, then you do not have to write so many things about it, right. So, and the scope of applications is in all different disciplines we have, right. We have application in industry, we have application in art and entertainment, we have also application in education, right, medicine and so on. So, the scope is very, very wide. Okay. Now, so the basic elements, if you look at the way we had defined the contents of the course, right. So, maybe we can again look at the broad three elements in computer graphics. What are these? These are modeling, where we try to define the shape of the object, and what do I mean by shape is basically the geometry of the object or the scene, right. So, what are the different representations we require in which we can have the shape or the geometry of an object. So, that is what modeling is all about. Then we are looking at rendering. Rendering, as I said, is a way to display objects, which in turn includes not only to decide what is to display, right, but also the attributes of display, right. So, for instance, we are going to talk about shading of an object, right, illumination on the object, what is the color of the object or the texture of the object, right. So, all these attributes also have to be incorporated when we are talking about rendering, okay, because one of the motivation we have is to be able to do the rendering as realistic as possible. Okay. And then the third element or the component, which is, as I said, is animation, where we are addressing the issues of movement and dynamics. Okay. So, this could be movement and dynamics of the objects of the scene, this could be movement or dynamics of other parts of the scene, for instance, camera movement, that also gives a notion of movement of the scene, okay, or maybe change of the attributes in the rendering, that will also give you some notion of the animation, right. It is basically evolution over time of the scene, right. Okay. So, these are some examples of modeling, for instance. So, we have examples, let us say this is some engineering part, right, where we have collection of primitives. There is a disk, there is some cylinder there, and there are other simple primitives. So, it is an assembly of primitives together, okay. And then there are operations which could have union of them, right, subtraction of them, and so on. Okay. So, this is one way of dealing with modeling. So, assembling of primitives and operations of these primitives. Okay. Now, there could be situations where we want to have models of structures which are not so regular as we find in engineering applications, right. For instance, a face, that is a fairly irregular structure. Okay. Then the question comes, how do we represent it? So, one way to have a representation could be have a collection of points, right, and the connectivity of these points, okay, which we call it as mesh, right. So, it is through mesh, and this is showing that you can have a notion of sampling of these points or the resolution in which you specify the mesh. So, here you see a dense mesh and here you see a coarse mesh, okay, and that governs, let us say, the faithful reconstruction which you have for the face, right. So, there could be instances where this is better suited, where there could be instances where this is better suited. Okay. Then there are also structures where we need to have a continuous representation of the geometry, right. So, here when you see a structure like this, what we have is a continuous surface, more or less, right. So, there are ways in which we can have definition of surfaces which would adhere to the continuity criteria we prescribe. Okay. So, for instance, the parametric surfaces, you may have heard the names B-spline surfaces and so on, right. So, these fall into this category. So, we are going to look at those also. And then there are structures which we have of this kind, right. So, here what we have is there is a structure something like which is spherical in nature, and then these are some artifacts to that structure. Okay. So, we can also look at this as a definition of a function defined on a spherical domain, right. So, we have implicit representation of a surface through these functions. Okay. So, these are called implicit surfaces. Okay. So, there is a range in which we can have the representation for the geometry of objects. Okay. And this is to tell you that all we are concerned here is the envelope of the object, right. We are not talking the inside volumetric representation, right. This is just the envelope. Rendering, if we look at, so this is an example where we have a rendering of a virtual scene with chair and so on. Now, this is just to illustrate that what are the issues involved. So, what you see that within this scene we have defined a camera, and this is the plane on which we project whatever is seen on this camera, right. So, what are we saying? We are saying that there is an issue of viewing what we have in the scene through the camera which is defined for the scene, right. So, therefore, there are issues as to what gets clipped within the frustum of this view which is defined through the camera. And then there are also issues is how do I render these objects, what is the shading I have, that is the interaction of the light source which I have in the scene, right. Things like shadows. Okay. These are all the rendering issues we have. So, here we see whatever is there of the scene with respect to this camera. So, this sort of simulates the process of rendering. Okay. And then you see on the walls we have this pattern, which is some sort of a texture to the wall, right. So, it is a texture mapping on the wall. Okay. Now, next, this is a favorite example I have is that look at these three images, right. So, as I said that we always try to attempt when we are doing rendering to have a high degree of realism. Okay. Now, if you look at these three images, the question is which one of them is the real image? This one. Okay. Fine. So, but the other images are not too bad. Okay. If I probably had not shown you this, you would not have made the difference, right. So, all it is saying is that the rendering using various attributes and aspects we have, one can achieve the quality of rendering as good as or as close as to the realistic rendering we have, right.
Isn't this just a light difference?
Yeah, of course, there are differences. There are light differences. There are texture differences, right. There are differences. Okay. So, this is an inspiration that we have a real image here, and I want to try to simulate this through computer graphics technique, right. Now, this is an example of animation, and so here what we are trying to show is that this cartoon shape what you see will do some movements, and so this is done here in the Vision Graphics lab. So, you can also see it from the web page we have. So, let me run this. Right. So, here in fact there are several things which you might have observed, that there was a motion of the camera, there was a motion of the character, right, moving hands, arms and so on, right, and all those things were put together. Okay. So, there are several questions as to when I need to do this animation of this character, let us say, right. So, I need to have a representation in such a way that I can perform the animation. So, when you look at this structure, it is an articulated structure, meaning that there are joints, there are segments, right, which I can move, and in turn I can move the envelope of this character, which I see it as outside skin, right, in association with my articulated structure which I have inside. Okay. So, there are several ways in which we can do this. Okay. So, now let us go back and see the historical perspective of computer graphics, right. So, if we see in 1963, that is where we got the first graphics workstation. Okay. So, it enabled to have the graphical output on the monitors. Okay. That is where we started. And then the first SIGGRAPH, which is a very popular event in computer graphics community, right. It is a special interest group in graphics. It is an ACM conference which was held first in 1969, right. So, since then it has been held every year. Okay. And then if you look at the activities which went in, let us say, 1970s, they were primarily concerning raster graphics, shading, illumination. Okay. So, rendering was quite emphasized. The trends continued even in, let us say, late 70s, and in early 80s, right. So, the emphasis has been in the realism of the rendering. Okay. And then in 1980s, particularly late 1980s, there was this notion of physically based animation. So, what does it mean is basically says that how do I inject the laws of physics to the process of movement, right. There are several situations where I observe a physical law governing the movement, right. If I throw a ball, it is a projectile motion and I know how to do projectile motion, right. So, there are many situations where we can incorporate laws of physics and do the animation. Okay, so, that was the motivation. The other aspects which we have is, so now in 1989 what we had, the first Academy Award given to a completely computer generated animation film, which was Tintoy by Pixar. So, Pixar is a animation company which does the computer generated animation films. And in 1990s, the emphasis was given to the interaction, scientific visualization, virtual reality, augmented reality, multimedia and so on. So, here in fact, what you see is broadening of computer graphics. Many aspects started coming in, right. By the nature of computer graphics, it is interdisciplinary in nature, right. But this was more sort of emphasized in 1990s. And in 2000 onwards, we have real time visualization of large data sets, right. So, what had happened is the concept of modeling, which was more, let us say, in the form of primitives and the representations for surfaces and so on, in fact started depending largely on the acquisition methods of data and geometry, right. So, they just put laser scans for acquiring the data. What it gave in turn is huge amount of data. Okay. So, then the issues were, how do we cope up with this data? Now, we have the way, or we have the data which can capture the geometry, but the data was so dense, then you have to have processes by which you can prune out the data and use it in a meaningful manner, right. So, issues like data compression, they also came, right, and also some combination of computer vision and computer graphics, right. So, if you look at the process of computer graphics, what do we have? We have input coming as a specification of the scene, right, where we have the geometry of the models and so on. Output, which is on a device, is an image, right. Whereas, computer vision classically is seen as, I have an image or maybe more than a single image, I have multiple images and I try to do the reconstruction of the scene or the model through those images. Okay, it is somewhat an inverse problem what we do in computer graphics. So, there could be several techniques which one can use from vision and from graphics and do some meaningful things, right. So, that is how the activity started in this area. Okay. Now, this was just a historical perspective. Now, let me also give you certain applications which are specific to say engineering. So, here what you see are various engineering parts. Now, these are helpful in a way that you can do lots of simulation, right. Instead of doing these experiments live with the actual parts, you can do simulations using these virtual parts, right. So, that is the way we can have the application of computer graphics in engineering. Similarly, we also have applications in medical things, right. So, here it is shown that what we can use the computer graphics as building tools which allow you the visualization of various parts or organs in human body, right. So, there is this project called Visible Human Project, where you have enormous amount of data in digital form, okay, in slices, and you can use that data to do 3D reconstructions of parts, right. So, these are the slices and this is the 3D reconstruction of this part, right. Okay. And here what is sort of shown here, you have this skeleton and some muscles which are on the top of that skeleton, and this is the envelope which is like the skin of this arm, right. And then you can add functional attributes to this in addition to the geometry which you have reconstructed, and again perform the biomechanical simulations, right. What happens if I move this skeleton? How does the muscle deform? How does the skin change, and so on, right. So, we can use computer graphics in the domain of medicine. So, this is a gross level of body structure we have, and these are the minute structures we have, for instance tooth, right, and we can look at the reconstructions of those. So, they can help us in the process of diagnosis of any abnormality, right, visualize them. Okay. So, this can be a good aid to the medical clinicians. Okay. So, similarly one can see applications in biographics, right. So, biographics meaning that we are dealing with molecules and molecular structures, right. So, we can have representations of various parts or atoms of a molecule and their connections or other functional aspects. Okay. So, and how does, for instance, protein represent it, right? What are the linkages of protein to the rest of the structure, and so on. So, one can also apply graphics in biology. Okay. Now, entertainment, of course, this is a sort of an obvious application, and we all see application of computer graphics in entertainment, right. So, you might have seen several of the special effects which are done through computer graphics. You might not have noticed that it was done through computer graphics, but you must have seen those special effects, right. So, this is you may already know what the example is. This is from Final Fantasy, right. So, let me just run this, and you can see that the amount of realism which has gone in. So, here again the issues of the amount of data which is generated, right, the amount of resources which are used up for generating the frames is enormous. So, this is a completely virtually created character. Okay. We still notice that it is not a real person, right, but we can appreciate the realism which it has even now, right. Okay. So, now if I see a, let us say, very gross picture of what we are talking about computer graphics, then I can look at basically this as a rendering process, right, and I can have a definition of a 3D scene, which in turn gives me a 2D image through this rendering process, right. So, all I see is that a conversion of the scene into an image, right. So, let us try to look at the anatomy of this process in a much more elaborate way and see this process as a pipeline. Okay. So, that is what it is, and that is what we will be looking at various stages in this course. So, what do we have? So, we have just elaborated that conversion we had from the 3D scene to 2D image. So, I have a 3D scene which in fact is constructed using various models, right. So, I have model 1 to model n, and I apply some transformations through which I take, let us say, model 1 to this 3D world scene, right. So, an example could be, let us say I want to do the reconstruction of this room. Okay. So, there are several chairs, there are people, right, and there are walls and so on. There are many things we have. Now, what I can think of is that since chair is a single object, right, then I do not have to do the modeling of every chair if I find that the other chairs are just an instance of one chair, right. I have a model of one chair, all I need to do is apply an appropriate transformation to that model, right, and put it in the 3D world. Okay. So, this modeling transformation is basically taking from the coordinate system I have specified for model to the coordinate system I have for the 3D world, right. So, once I take a chair to the scene, it does the transformation of this coordinates, right. Okay. So, and through that it enables me to specify instances of the same model. I can have various modeling transformation attached to this model and put it in this scene, right. So, once I have got this 3D world built up as an assembling of various models using modeling transformations, now I need to worry about how do I view them, right. So, let us say there is a situation where I am sitting, that is where I put the camera, right. So, once I have built the scene, by inserting the camera again gives me a specification of how do I want to see that scene, right. So, again there is a notion of transformation which is for the viewing of the scene, right, because this scene is going to be looked differently if I see it from this point, from that point and from other point, right. So, that is what we try to capture through viewing transformation. Viewing transformation in turn means that I specify the camera and the attributes of that camera into the scene. So, this transformation gives me another 3D scene, right, which has the viewing specification. Okay. Now, remember that the output is going to be an image, right. So, all these processes ultimately have to be mapped to something in 2 dimensions. So, there I need some mechanism by which I can project this 3D scene onto something which is 2 dimensional, right. And since I have specified the viewing or the camera, I have a way to perform this projection. Okay. So, here we are talking about how do I project this 3D scene to get this 2D scene. Okay. Now, once I have got this 2D scene, this could be in the representation I had used to define the word, right, which could be continuous representation of objects, right. Now, as I told you that ultimately the 2D image which we display is displayed on a raster device, right, which is nothing but collection of pixels. Then I need to have a process of rasterization where I will convert this representation, whatever I obtain in the 2D scene, to this 2D image. Okay. So, this is how the whole pipeline is for converting my 3D scene which I had to this 2D image. Okay. And each of these boxes we are going to study in detail. Right. Now, another view of, let us say, graphics more in terms of as a system. So, that was the process which we had looked at. Now, if I want to see it more as a system where I had the hardwares which are used for the system, I can see this as basically collection of some input devices, right, for instance keyboard, mouse and so on, a unit which has the capacity of processing and some memory in it, right, which does the churning, and then I have this what I call it as frame buffer, which is nothing but, as far as the representation is concerned, it is something like array of pixels, right. And so, what is the motivation of having this? As I told you that output display is something like what we have, for instance, CRT monitors, right. That is what you are used to, and these days we also have now TFT LCDs displays. Now, the idea here is that this processing whichever I do here needs to be mapped to this output display through this frame buffer, which is containing the information in something like raster forms, right, grid of points, grid of pixels, right, which I will map it to the output display whatever I have. Okay. So, this frame buffer which we have is nothing but something like collection of or grid of pixels, where the resolution, the spatial resolution gets determined by the number of pixels I want to display or I have, and the depth is the number of bits I assign for each pixel, right. So, this basically gives me the capacity or the resolution of this frame buffer, right, or the memory space I need. Okay. Now, let us try to see the linkage which we want to establish between this frame buffer and the output display. Okay. And then later on we are going to look at the input devices, what kind of input devices one may use, right. Okay. So, you are familiar with CRT displays, cathode ray tubes, right, you know what it is, you know how it works, right, more or less. Okay. So, what is happening is that these are some sort of deflection plates we have, and there is this phosphorus coating on the screen which basically gets on and off, right, with a refresh rate of 60 hertz, right, and that is why we can't see the discontinuity, right, we are not able to visually perceive it with this rate. Okay. So, one can actually look at these display devices into the category of raster scan displays and the random access displays, right. So, raster scan is that I am basically doing a scan wise display, right, from the top to the bottom, and random access is that I do a display in a calligraphic fashion. So, wherever it comes I just put that on, right. So, again in the case of raster scan display, I have what we call it as non-interlaced and interlaced, right. So, non-interlaced means I go every scan, right, one scan after the other one. In interlaced, I basically do a half scan first and then the other half, and this half is decided by I do a first, let us say, odd scans and then I do even scans, right. So, this may increase the effective rate of refresh, right, and that is what is done in many of the monitors we have, right. It is interlaced.
Is the resolution also affected?
Resolution is not really affected, because as I said that the time which we are taking to do the display, right, is very, very short. So,
in effect at a time only half of the bits are being scanned.
right. So, but you know the visual difference as far as is concerned, it is not so much, okay, because I am going to just see one scan and then the other scan, right. So, it is a result of two scans eventually which gets to my impression, right. That is what gets aggregated when I perceive it, right. Okay. So, now what we are looking at is some sort of an interface which takes us from the frame buffer, right, which is a grid of pixels or the array of pixels, and the CRT display, right. So, this, as we know that it is an analog kind of a device. So, now what are we trying to say, that we are going to take some value of the point here, which is a value for the pixel which we want to display, and map it to this, right. Now, one can think of that the information where here we have, there is a register for the same number of bits I specify here for a point or the pixel, right, and I have a digital analog converter, right, which takes this value of the register and puts into the appropriate analog value I need for the change of the voltage or whatever, right, for this, fine. So, now what we are saying is that if I have the bit planes, so bit planes means the number of bits I specify per pixel in this frame buffer. So, the bit planes in turn gives me the range of the intensity value I can have, right. So, if I have n bit planes, it means I can have these many intensity values 0 to 2 to the power n minus 1. Minus 1 should be here, 2 to the power n minus 1, right. Okay. So, now let us say I pose this as a question, that instead of having, so what is happening is that the range of my intensity of the color I want to have in my CRT device gets completely determined by the number of bits I assign per pixel in the frame buffer, isn't it? Now, let us say I want to augment this, right. That means, though I had, let us say 3 bit value here, so I had a 3 bit register here, right, which would have given me 8 values, but instead of 8 I want to have 60, or the range of the intensity, right, something which I can have as a 4 bit pixel value, right. So, how do I augment that? So, one way is that what you can do, what have you heard the name lookup tables, right. So, lookup tables are good way of handling this. What happens is that, let us say this is the scenario, I have this frame buffer, right, where I take each of these bits, right, and I have a register here which is 3 bit register. So, depending on the value of this register, which earlier was getting mapped to the intensity value, now I do something different. So, I define a lookup table for which I have clearly the width of this larger than the number of bits I have for the register, right. That is where I will do the augmentation, right. So, what do I do? I use this value in this register just an index to the table. So, I do not use this as an intensity value, but I use this as index to the table, and in that table I have the entry of the width of my choice, right, which is larger to the size of the frame buffer, right. So, this way I am augmenting the intensities, is not it? The only limitation is, what is the limitation I have?
The number will be still, the number of colors you can have will be still the bits in the register.
Right, right. So what is she saying? That simultaneously, if I want to look at, I can still have those many colors, right. I can have only 8 colors, right, but the width of them or the values can range from 0 to 15 if I have a 4-bit width of a lookup table, right. But that may not be a big constraint. You may still want to use limited number as far as the colors are concerned, but what you want is the width to be more, right, or the number of bits of per pixel to be more, right. Okay, so maybe we stop here. So, next time what we are going to look at is, in the graphics system we had looked at, right, what are the input devices, how do we look at the functionality of those input devices, okay, and then look at the entire rendering pipeline going from the end of it, right. So, we will do the traversal of the pipeline in a reverse order, right. For instance, studying the rasterization process first, okay. All right, thank you.